Alright, let's see if we can discuss linear combination and spans. Now when we talk about linear combination and spanning, we can talk about this in the context of many things. We can talk about it with vectors, with functions, with matrices, and anything that would fit into a category called a vector space. Now I know we didn't talk much about vector spaces, but examples of a vector space are vectors, vectors in R3, vectors in Z2, any of those vectors. Other functions of vector spaces that we won't go over in linear algebra are functions. Functions form a vector space as well. We do talk about that in differential equations. And then we're currently talking about matrices, so the idea of matrices as a vector space is also something that we don't really dive into, but the concepts of vectors, such as the linear combination and span, apply to matrices. So let's take a look at linear combination and span of vectors, and then let's look at linear combinations and spans of functions, and then we'll finally look at linear combination and spans of matrices. So for vectors, for the sake of trying to visualize them, let's talk about vectors in R3. So here's my first example. Let's take a look at the vectors 1, 1, 1 and 2, 2, 2. Now these two vectors are vectors in R3. And if you can't already see it, they are actually linearly dependent. If you multiply the first one by 2, then you're going to get exactly the second one. So they're linearly dependent. So let's take a look at the linear combination of these two vectors. So when we talk about the linear combination of these two vectors, we are looking at a scalar, a real number a, plus b, well, a times the first vector plus b times the second vector. Well, so that's what it means when we say a linear combination. And really, that's all there is to it. So that's a linear combination. A linear combination is the sum of a scalar multiple of each of those vectors. Okay? So a more interesting idea or concept is to say, what is the span? So the span of these two vectors, or the span of these two vectors, is any vector that can be written as a linear combination of these two vectors. So one way to describe that could possibly be what kind of vectors can we get? What kind of vectors x, y, z can we get by writing the linear combination of those two vectors? Okay, so we're interested in x, y, z. Well, if we do the addition here on the left-hand side, what do we get? We have a plus b. So I'm going to rewrite this like this. A plus b, and then the second component will exactly be the same, a plus b, and the third component will exactly be the same, a plus b. So what we can do is we can write a plus b, well, we can write a system of linear equations, but they all come down to a plus b is equal to x and then a plus b is equal to y, and then a plus b is equal to z. So any vector that has the exact same x, y, z components will be the span. So we can say the span of these vectors, I guess we can specifically say which two vectors we're talking about. The span of these two vectors is the set. So we can write it as set now. We can say the set looks like x, y, z. Well, instead of writing x, y, z, maybe we can write it as x, 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 since it's all the same. Where x is a real number. So, so that's a span. Now, if you can imagine how this thing might look like, this thing would look like a line in three-dimensional space. We can actually, instead of calling xxx, we can call it 111, where this whole vector 111 is actually being multiplied by t. Now, if we just change it to that, then we can express this as a line. So the line would look like this. L of t equals t or t times 111, or if you want to write this in parametric form, it'll be x equals t, y equals t, and z is equal to t. Okay? So the idea of looking at this as an example is to look at how this would look like visually, because this is something that we can still visualize. So these are the two vectors, and if we were to add them together, it would just simply span that line. So if I write my equation of a line and then try to find how the vectors might look like, I'll use n because that's a built-in n times 111. I'll use n instead of t because that's a built-in parameter for this. And then if I let my n go from minus infinity to infinity, I can't go that far, but let's go minus 10 to 10. This is how my equation would look like. And if you look at that arrow that's changing back and forth, it's exactly a line. It forms a line. Okay? So maybe I'll freeze it right here. And then again, let's take a look at that line being shrunk, going the other way. So that's the linear combination of those two vectors. So it spans a line, a one-dimensional space in 3 dimensions. So even though we had two vectors, 111 and 222, it still only spans a one-dimensional thing, even though we're in R3. Okay? Alright, so that's the first one. That's the first example. We've got a few more to go here. Let's take a look at another example where you have um, 1, 0, 1 and 0, 1, 1. You can use inspection, but you can actually prove this as well, that these two vectors are in fact linearly independent. Alright, so let's see how to deal with this. Linear combination. Let's first start by linear combination. And the linear combination is just simply writing this as the sum of a scalar times each of those vectors. So when we talk about linear combination, we can essentially stop right here. That's a linear combination of those two vectors. Alright, now let's take it a step further and find the span. And the span of this is what we would get. What is this equal to when we take the linear combination of those two vectors? So what we can do is we can imagine what kind of x and y and z values are we going to get by adding these two vectors, or by adding the scalar multiples of these two vectors. Well, let's see. We can go ahead and write this out. And let me just do some modifications here. So we add a times 1 plus 0 times b. We add 0 times a plus b times 1. And we add 1 times a plus 1 times b. So we get a system of linear equations that look like this. So we can actually write this as a system of linear equations. A is equal to x, b is equal to y, and a plus b is equal to z. So since we know what x and y are, we can just say x plus y is equal to z. And that combines all three of them. Oops. So what I wanted to do was, I wanted to just write x plus y is equal to z. So that looks like it describes our x, y, z, and that also, I hope, to people look like an equation of a plane. So x plus y is equal to z looks like an equation of a plane. So it looks like the span of these two vectors is the plane that's described by x plus y plus z. Okay, so why don't we write that out? So the span of these two vectors is, we can say, is the set of real, it's a set of x plus y is equal to z combinations in R3, but we can also simply write is a plane. And then we can just write x plus y is equal to z. Alright, so let's get a visual of that. Here are the two vectors. And what I did was I had a linear combination of them and then I added them. So let me take A, that's the vector A, and then I'm not adding B to it, so I'm just taking the scalar multiples of A. And then if I add B to it, then I'll start moving around between these two vectors. So if you imagine these two vectors, they span a plane. Okay, so now that black vector that's moving between those two vectors would describe any vector that is a linear combination of those two. So if it's still hard to visualize, what we can do is we can actually write the equation of that plane. What is it? X plus y is equal to z. And let's make this a little bit transparent so we can see it. And then maybe even brighter. Let's make it yellow. And let's spin it around for the meantime. And if you can see that every single vector that we have here is on that plane. So that linear combination vector is a black vector. Let me take everything else out. So those two vectors I took out are the original vectors, and then I have each of those original vectors stretched out, and then I added those two original vectors. So the sum of the scalar multiple of those two vectors is still here. It's in black. Let's look at it from this perspective. That's that vector. And then as I change those scalar parameters, I see that I'm staying within that plane. So let's take a look at it from this angle where we can see if it jumps out of the plane, and here in fact it doesn't. It stays on the plane. Well, the plane goes infinitely forever, so you can imagine that that vector is still on the plane. Okay? So that's what it means to span something. If you have two vectors in R3 that are linearly independent, they will span a plane. They will span a two-dimensional vector, or two-dimensional thing, two-dimensional space. Alright, so that's the span of that. Now, if we take a look at what happens when you have three linearly independent vectors. So if you have three linearly independent vectors, we can go through the same process, but if you can imagine just anything, this will span every single thing in space. Let's see how that would look like analytically. Let's first talk about linear combinations. So the linear combination of three vectors is going to be the sum of those three vectors being scalar multiplied and added together. So we can say that the linear combination of these three vectors looks like this. Now, if you want the span of this, then we essentially copy that. And then we ask ourselves, what kind of vectors are we going to get out of this if we do the linear combination of these things? So again, we can call that x, y, and z and ask ourselves, what kind of x, y, and z values are we going to get? Well, let me copy this. And then change this right-hand side where we have a plus 0b plus c. And then we have 0 times a plus b plus c. And then we have a plus b plus 0. So we basically have a system of linear equations that look like this. And we want to know what x and y and z are going to be representing. So a plus c equals x. B plus c equals y. And then a plus b equal to z. So this is a little bit more challenging or more interesting. What we can do is we can think about writing this as a 3 by 3 matrix with augmented with a x, y, z. So let's see how this is going to look like. So I'm going to first write this in a 3 by 3 matrix. And then I'm going to augment it with a 3 by 1 vector. And so my coefficients are going to be, I want to solve for a, b, and c. My coefficient for a is 1, my coefficient for b is 0, and my coefficient for c is 1. And then this is supposed to be my x. And then I have a 0, b times 1, c times 1, and then a 1 times a 0, 1 times b, and then a 0. Alright, so this is now my system. It's become an augmented matrix. Let's see if we can do some row reducing. If we row reduce, let's use operators here. So we will take -1 times row 1 and then add it to row 3. And say we're going to replace row 3 by that. And so what's this guy going to look like after we do the transformation? This is going to, everything will be exactly the same except this will be 0. This will remain 1. This will be -1. And then I did something here too. I added negative times row 1, so we got a minus x. Okay, so now let's do the same over here, but this time we'll multiply negative row 2, and then we'll replace row 3. So this would make this into a 0. This will make this a negative 2. And this will replace this into this minus x. Alright, so it looks like we have something in row echelon form here. So this is a little trickier to manage, because now we have x and then y, and then z is equal to x, or z is equal, or not equal to, but negative 2c is equal to this thing. Now the unfortunate thing about this is that we're not able to see a relationship of what x and y and z are equal to. We're not saying that x is equal to y or anything like that, because there's no relationship like that. So in this case, there's no relationship between x and y and z that would make us describe something in R3. So in this case, we just have to say that the three vectors span anything that we can think of, any combination of x and y and z. So remember, the key here is that we cannot find a relation between x and y and z that would restrict the three variables. And so this must span all of R3. Okay, so if we look back up here in our previous example, we're able to get A is equal to something, and the combination of that got us a relationship between x, y, and z that restricts the choices of x, y, and z. X and y are kind of independent, but it restricted the choice of z. Over here, we didn't really come up with that equation. We didn't quite finish it, but we're not going to come up with that equation, so it doesn't look like that's going to work for us. Alright, let's take a quick look at power functions when it comes to linear combinations and spans. I have 3 examples here. To get a linear combination, again, it's really just taking these things and then writing a scalar multiple. So let's multiply 1 times A, and then we'll just multiply the second one times B and add it, and then multiply the third one times C. So regardless of how you write it, ax squared plus bx plus c, or in this case I happen to have written it backwards, a plus bx plus c x squared, this is a linear combination. So the span of these 3 vectors, I'm calling them vectors because they technically are vectors if we look at it from a vector space point of view, but they are functions. So span of these three functions, or these three vectors, is any quadratic function. So if you think up of any quadratic function, then that's a span. Actually, if c was equal to 0, then it's not just a quadratic function anymore. So any quadratic function, linear, or constant function. Because we have to account for any of these things being equal to 0. So if c and b were both equal to 0, then it would just be a constant function. So so that's about all we can say about these three functions. Let's take a look at another example. What if instead of this we don't have this b in the middle, or we don't have the x. So this could be a quadratic function, or if c was equal to 0, it would be a constant. So there's no room for linear functions here. Not only that, but if it's a quadratic function, it does not have a linear term. So any quadratic function that does not have a linear term. So I'm only allowed like 4x squared plus 3, or x squared plus 1, or 25x squared minus 16. So any of those combinations that look like this, where c is not equal to 0, is a quadratic function that does not have a linear term. And if c was equal to 0, then this whole thing is gone, and so all you have is a constant function. So the span, oops, let me get rid of that. So the span of 1 and x squared as functions would just be things that look like this. Okay? So our last example for functions would be this. It doesn't have to be polynomials. These are examples of exponential functions. So let me just copy this. Well, let me just do it on my own here, I guess. We can so the linear combination would essentially be these functions, or vectors, where we multiply the first one by some constant, multiply the second one by some constant, add it to the first one, and then multiply the third one by another constant. So this is a linear combination. So the span of this, and this is a case where there's not really much to describe. The span of this would be the set of any function, let's call it f of x, equal to this, where a, b, and c are any constants that could also be equal to 0. So I know it's not very descriptive, but that's the best we can do with a span. Oops. Okay. So those are simple examples of functions, and I'm hoping that the idea of a linear combination of span is starting to make sense now. Alright, so So let's take these ideas to a vector space of matrices. And here are a couple of examples. Alright, so let's do the span, or linear combination. So the linear combination of these two matrices would, just like we've been doing, would be a constant times the first one plus a constant times the second one. So that's a linear combination. Well, now let's ask, what is the span? So the span of this is going to be, what would we get if we added these two matrices? So what values of x or w, x, y, and z do we get when we add these two matrices? So to try to dig a little bit deeper, what we can do is we can add these two things, A times that first matrix and B times that second matrix, and then try to express that with A and B. So we have A plus 0 for the first slot. We have 0 plus B for the second slot, 0 plus B for the second slot, and then A plus 0 for the fourth slot. So this is your matrix. Well, A is equal to W and A is equal to Z, and so W and Z must equal each other. And then X and Y must equal each other. So we can conclude that the span of these two matrices is the set of matrices of the form. So I'm going to go ahead and copy this matrix, but then we changed a few things, right? We changed that. We said that Z is equal to W, so we can just say W and W for that, and X is equal to Y. So we can just say that. So any matrix that looks like this so the span of these two matrices is a set of matrices of the form that looks like this. So W, the diagonals are the same and the wings are the same. Okay. Alright, this looks vaguely like it was a symmetric matrix, but for symmetric matrices, the W's don't matter. The only thing that matters would be on the opposite sides for the wings. So let's see if we can span the set of all symmetric matrices, not just when the diagonals are the same, but it's all symmetric. So we're kind of done with the linear combination and span of this one. Let's take a look at another example. This time, let's use three matrices and try to figure out what the linear combination and span is. So first, linear combination. So the linear combination would be, and like we've done before, would be multiplying the first one by a scalar, multiplying the second one by a scalar and adding that, and multiply the third one by a scalar and adding that. So linear combination would be these things. Now let's find the span. So the span is going to be asking you the question, what is the linear combination of these three matrices, and what would it look like if we arbitrarily called it W, X, Y, and Z? Alright, so we'll set it up the same way. If I look at the left-hand side of this equation, I see A, 0, and 0 for that 1 by 1 slot. The 1 by 2 slot gets 0, 0, 1 times C. The third slot gets 0 and 0 and 1 times C again. And then the fourth slot gets 0, B plus 0. Alright, so if you look at this, it looks like W and Z are now independent of each other, but X and Y are the same. So we can actually use this for a span, but since we assigned W, X, Y, Z to it, let's just see that X and Y have to be the same, so you can call it X or you can call it Y. But either case, we're ready to report the span of these three matrices. So the span of these three matrices is the set of, now if we look at this, it looks like all symmetric matrices now. A and B are not restricted to being equal to each other. They're independent from each other, but the wings have to be the same. So it's a set of all 2 by 2 symmetric matrices. And then we can even express how these symmetric matrices would look like. We can say W, X, X, Z, or we can say A, C, C, B, or whatever letters we use, as long as the wings are the same and diagonals don't necessarily have to be the same. Alright, so that's a quick overview of linear combinations and span and what they mean to each other. And so I hope the process makes sense and what we need to do in order to describe the linear combinations and the spans of these things. We will dive into more theory when we talk about linear combinations and spans of vectors. Okay, I hope this helps.